Okay, so all of our basic limit laws hold for infinite limits. So, in order to be able to evaluate infinite limits exactly, we need to be able to build them up out of sort of more basic limits. Now, I already showed a couple, arctangent, e to the x, but one of the most basic ones we want to be able to deal with are powers of x. And what we have is the following. If we let r be an exponent that's greater than 0, then the limit as x approaches infinity of 1 over x to the r is equal to 0. If r is a rational number with an odd denominator, then we can also plug in negative values into x. And as x goes to negative infinity, 1 over x to the r also goes to 0. So here are the three graphs of these sorts of functions. If I have a rational number with an even numerator and an odd denominator, then I have a function that looks like this. It looks kind of like 1 over x squared. And as I go to the right or the left, I approach 0. If I have m over n, where both of them are odd, it looks kind of like the graph of 1 over x to the 1, just 1 over x. It's positive for positive values of x, and negative for negative values of x, but to the right and to the left, we're approaching the x-axis, y equal to 0. And otherwise, if r is not of this form, then we can't take x to the r for negative values of x, so the function's undefined to the left of 0, but to the right of 0 it looks like this, and it approaches 0 as x goes to infinity. Alright, so given our basic limit laws and the fact that I just wrote down, we should be able to evaluate the limits at infinity for any rational or algebraic function. So let's look at a fairly typical example. Let's look at 3x squared plus 2 over 2x squared minus x and take the limit as x goes to infinity. Your first idea might be, hey, let's factor out the denominator here. Well, I'm going to tell us not to do that. There's no reason to do that. Well, why do we factor out in some of the previous problems that we dealt with? The reason is because as x approached whatever value we were looking at, the denominator often went to 0. And by factoring, we hope to cancel terms so that our denominator no longer went to 0. However, we're letting x go to infinity here. So 2x squared minus x is most definitely not approaching 0. In fact, it's going to get arbitrarily big. So no, we're not going to factor out because canceling factors doesn't accomplish anything. Instead, our idea is going to be to turn this denominator into something that instead of approaching infinity is now approaching a constant. And the way we do that is we divide everybody by the largest factor, the largest term that we see on the bottom. Specifically in the case of a rational function like this, that means we're going to divide by the highest power of x in the denominator of the expression, and the highest power is x squared, as I see right there. So I divide everybody on top and on bottom by x squared. Effectively, I'm multiplying by 1. And so that gives me, after I simplify, 3 plus 2 over x squared all over 2 minus 1 over x. Now the bottom is going to be something that is approaching a constant, and then we'll have to see what's happening on top. Now, just this one time, I'm going to explicitly sort of show the limit laws going on. This is the limit of a quotient, so I end up with the quotient of the limits. I have the limit of a sum, which turns into the sum of the limits, and the limit of a difference turns into the difference of the limits. And also, this is a constant multiple of 1 over x squared, so I'll pull the 2 out of this limit to give myself the limit of 3 plus 2 times the limit of 1 over x squared, all over the limit of 2 minus the limit of 1 over x. Great. Now on top, I have two constant limits, and I have two limits of reciprocal powers of x, which we just said went to 0 as x goes to infinity. So this goes to 0, this goes to 0, and I'm left with 3 plus 2 times 0 over 2 minus 0, which is 3/2. Okay, so now let's evaluate the limit as x goes to negative infinity of 2x plus 3 over 5x cubed plus 2x. If you'd like to, pause the video for a second and see if you can do it yourself. Otherwise, let's just keep going. So what we did last time was we divided by the top and bottom by the biggest power of x on the bottom. Here I see the biggest power of x is x cubed, so I'm going to divide everybody on top and on bottom by x cubed. We get 2x over x cubed plus 3 over x cubed over 5x cubed over x cubed plus 2x over x cubed. When I simplify that, that leaves me with a limit as x goes to negative infinity of 2x cubed plus 3 over x cubed all over 5 plus 2 over x cubed. Again, what I'm accomplishing here is turning the denominator into something that is approaching a constant. 5 plus 2 over x squared, and I know that reciprocal powers of x go to 0 as x goes to plus or minus infinity. The top in this scenario does not have a constant, it just has two reciprocal powers of x, 1 over x squared and 1 over x cubed. As x goes to negative infinity, each of these guys will go to 0. So skipping over the limit laws this time, the limit is 2 times 0, because it's 2 times something going to 0, plus 3 times 1 over x cubed gives me 3 times 0, all over the limit of 5 is 5, plus 2 times 1 over x squared gives me 2 times 0. And once I simplify, I get 0 divided by 5, and 0 divided by anything that is non-zero is 0. So here's question 2. Evaluate the limit as x goes to infinity of x squared minus 2x plus 1 over x squared minus 1. This is a slight trick question. It looks like maybe you want to factor this. Why? Because, well, you can factor the top and the bottom. However, I want you to answer one more question. Why don't we need to factor in this problem in order to solve it? Okay, now let's look at an algebraic function. Let's evaluate the limit as x goes to infinity of x plus 1 over the square root of x squared plus 1. Now when I have something like what I've got here under the denominator, I'm still going to be looking for the highest power of x, which here is x squared. However, it's underneath a square root. So in effect, the bottom doesn't really look like x squared. It actually looks like the square root of x squared, or x. So we're going to treat this just like the rational function problem, except our highest power is x squared underneath the square root, which is equal to x. Since x is positive, x is going to positive infinity. So I will divide the top and bottom by x, which is the same as multiplying by 1 over x. And I'm going to note that 1 over x is equal to the square root of 1 over x squared. So now when I distribute, up top I get x over x plus 1 over x, whereas in the bottom, to get it underneath the square root, 1 over x becomes 1 over x squared. So I get x squared over x squared plus 1 over x squared. Now I simplify to get 1 plus 1 over x over the square root of 1 plus 1 over x squared. Now I'm going to use my limit laws to break this up into a ratio of limits. I can put the limit underneath the square root, and I can break the limit up along the sums to get the limit of 1 plus the limit of 1 over x, all over the square root of the limit of 1 plus the limit of 1 over x squared. 1 over x goes to 0 since it's a reciprocal power of x. 1 over x squared also goes to 0 since it's a reciprocal power of x. And 1 and 1 are constants, so I'm left with 1 plus 0 over the square root of 1 plus 0, which is 1. Let's do the same problem, except let's let x go to negative infinity. Now we're going to do the same thing. The highest power on the bottom is x squared, but it's underneath the square root, so we're going to treat it like the square root of x squared. However, as x goes to negative infinity, when I take the square root of x squared, I have x negative. The square root of x squared is going to be the negative of x. Why? If x is negative, then the negative of x is positive, and the square root is always the positive square root. So since x is less than 0, the square root of x squared is negative x. So I do the same thing. I multiply the top and bottom by 1 over x, and when I bring the 1 over x underneath the radical this time, 1 over x is equal to the negative of the square root of 1 over x squared. So that means that when I bring that inside, I end up with a negative sign out in front on the bottom. But otherwise it looks the same as last time. X over x plus 1 over x, all over negative square root of x squared over x squared plus 1 over x squared. I simplify to get 1 plus 1 over x, all over negative square root of 1 plus 1 over x squared, and then I can evaluate the limits. 1 over x goes to 0, 1 over x squared goes to 0, everything else is a constant, so I get 1 plus 0 over the negative square root of 1 plus 0, which gives me negative 1.